All right. So in this module, now that we've talked about what fracture toughness is and how to increase it, I want to talk about how we can measure fracture toughness. So one of the common ways that we can study fracture and fracture toughness under more severe conditions is known as a impact test. And so you may have seen one of these before. It sometimes goes by the name of a Sharpie or IZOD test, but it's a quite simple test. We first make our material, which tends to be cube square cross section rod with a notch in it. And so this is one of those sharp notches. And so this notch basically mimics the flaw size, a surface crack. And so when we have that sample ready, we load it in the machine. Either if it's IZOD, you load it like this, or Sharpie, you load it like this. So essentially, we're going to apply a force to the top part of this bar, and the other part is fixed in the machine. Here, the sides are fixed at 2 points, and then it's impacted from the back in kind of a similar to a 3-point bend. You can also use a bend test, but we're going to talk about this impact test. And so then at that point, this hammer is brought down to the material with this swinging pendulum. So basically, the hammer is the part that impacts both of these test samples, and it's attached to a pendulum. And the change in height is a measure of how much energy it takes from the potential energy of the pendulum. So it basically uses the principle of a pendulum to impact a sample at high strain rates and cause fracture. And the amount of energy it takes is related to the fracture toughness, how much energy it takes to fracture the sample. So this is a common way, and it's a fairly straightforward way to measure fracture and fracture toughness. There's another way. There are many ways, but this is another way that we can measure fracture toughness, and it comes from an indentation. So this is similar to a hardness test, and in fact, this is a Vickers hardness test. And so it's a diamond shape cube, as you can, or sorry, square, as you can see here. We do that test, and not only do you get the indentation, but because you initiate fracture with these brittle materials, there is also cracks that radiate out from the indentation on the corners like this. And so the length of those cracks in conjunction with the force and the indentation made can be used to calculate the resistance to brittle fracture and therefore fracture toughness. So we can get K1C from the crack opening of an indentation either through Vickers or another micro hardness test as well. All right, so an important thing to mention when we're talking about measuring and we're talking about fracture toughness is to note that even ductile materials can sometimes fail in brittle ways. So the example I have here is the Titanic, as you may be aware, impacted an iceberg, very cold conditions, and the ship failed in a brittle manner because the steel that's constructed is typically ductile, but may change based on temperature. And so things that are normally ductile cannot always be assumed to be ductile. And that's where we get to this idea of a brittle to ductile transition. And this is something commonly detected by impact testing. So you can kind of do this test with an impact. So you can basically get your samples at a given temperature and then test them at those temperatures through this impact test to see where the impact energy changes, right? Because a ductile material is going to absorb a lot of energy before impact, whereas a brittle material is going to absorb very little. And so we can see that transition. So if we look at ductile materials, which is the green line here, you see that there is some change. It decreases a little bit with lower temperatures. But for the most part, it's very high impact energy. So these are things like FCC and HCP metals, so copper, nickel. And then we have high strength materials that are rather brittle. And you can see that they also can exhibit changes, but they're pretty subtle. And so they always kind of have low impact energy. However, you can have things like BCC metals, the lower strength steels, and also polymers that are ductile as well, where at high temperatures they follow the ductile behavior, and then there's this transition, kind of an S-shaped curve here. Then there's a transition at a specific temperature to the brittle, and so as temperature decreases, the energy they can withstand before fracture decreases, and so they become more brittle. So this is obviously important if temperature is going to be an issue with the application. So that's something that we have to consider. So, obviously the Titanic, it wasn't planned for those kind of temperatures, and obviously that's an issue if you're going to be in freezing waters. So that's something to mention. And also, when you look at the surfaces of the fracture material, so this is a notched sample, and it's the two surfaces after. And you can see that if we go up to these really high temperatures, so this one is 79 degrees, you can see it's a fairly rough, and there's a lot of deformation in the sample. You can kind of see that this change in shape over here. It was normally a square. And then as you go lower, you'll notice that it becomes smoother and more square, right? And it follows the shape that it was before. So doesn't have that plastic deformation like these higher temperatures do. And so that's where we kind of following this temperature. So this negative 59 is down here, and this 70 is up here, and then you have a transition in between. So that can be measured by taking impact testing at different temperatures for a sample. And this is obviously something that's important, not only for brittle materials, but for materials that can become brittle with temperature. So that's something else to consider when we're talking about measuring fracture toughness.